On number 8, we're going to graph the function, and the way we're going to do that is to sketch it using the things like intercepts, where it's increasing, decreasing, local maximum, minimum, concavity, inflection points, and asymptotes. So all these things are going to be things that I list out when sketching the graph. So first things first though, let's go ahead and have the derivatives at our disposal, since it can take quite a long time to find the first and second derivatives when we have to use them. So I'll go ahead and have those there, and first thing I'm going to do is find the domain of this function. To find the domain, we have to look at where the denominator is equal to 0. So that means x minus 2. X equals 2 is not in the domain. So our domain is everything from negative infinity to 2 and everything from 2 off to infinity. So what we really just want to keep in mind is that that 2 is not in the domain if it does show up later on. So next thing let's find our intercepts. Let's start with the x-intercept. And like we've always done before, finding the x-intercept involves setting y equal to 0. Okay, and so really, in cases like this, it's really just going to involve the numerator, because if we did multiply through by the denominator, it's going to go away. And we're just going to have 0 equals 9x, which tells us x equals 0 is an x-intercept, 0, 0. We should basically see the same thing happening with a y-intercept as well, but that would involve plugging 0 in for x. So 9 times 0 divided by 0 minus 2 squared would equal to 0 divided by 4, or just 0. So 0, 0 is also the y-intercept. Now we're going to look at the asymptotes. We're going to start with the vertical asymptote. Vertical asymptotes again are going to come from the denominator, x minus 2 equal to 0. So x equal 2, just like we found for the domain, is going to be our vertical asymptote. For the horizontal asymptote, I'm just going to take a shortcut to this one, since the function is made up to be something a little bit different. We notice that the degree of the denominator is 2, and the degree of the numerator is 1. So since we have a bigger degree on the denominator, then we know that the horizontal asymptote is y equal to 0. This also tells us that there are no slant asymptotes on this one. And now the next step to take is to find out where this is increasing and decreasing. And for that we have to find the critical values. And the critical values are going to be made up of the two things, where the first derivative is equal to 0 and where the first derivative is undefined or does not exist. So starting with where the derivative is equal to 0, I had the derivative provided for convenience. 0 equals negative 9 x plus 2 divided by x minus 2 squared. Okie doke, well, pretty much the denominator again is just going to go away. So we can cancel that out. We have 0 equals negative 9 x plus 2. So we have basically then x plus 2 is equal to 0, and x minus 2 is a critical number. Where the function does not exist is going to come again from the denominator, where it's equal to 0, and that still comes back to the x minus 2. And so x equals positive 2 is a location where the denominator is undefined. So these are our two critical numbers, and when we're trying to determine where the function is increasing or decreasing, we'll set that up kind of like on a number line, and then choose some test values to see what's going on around each of these critical values. Test values I chose were -3, 0, and 3. And so we're going to test each one of these intervals based off of the first derivative to see if we get a positive derivative for increasing or a negative derivative for decreasing. Okie doke, so here's our test values, and we're going to plug these into the first derivative. F prime of x is equal to -9 x plus 2 divided by x minus 2 squared. Now plugging in -3 to the first derivative kind of looks something like this. Now if we calculate this out, on top we're going to get a positive number. Underneath we'll have a negative number, and that's a cubed on the denominator, by the way, x minus 2 to the third. So when we do that calculation here, it's going to come out with a negative number, which tells us this is decreasing. If we plug in a 0 for x, on top we'll get a negative number divided by negative, so should have a positive value, increasing. And then finally, if we plug in the 3, we'll get a negative on top divided by a positive, so it turns back to negative and decreasing. So now we can see where this is increasing, decreasing, and constant. It's increasing on the interval between -2 and 2, and it's decreasing on the interval from -infinity to -2, union with 2 to infinity. Another thing we can then tell is, notice how these numbers are where it changes from up to down or down to up. So what we can talk about minimums and maximums based off of these numbers. But we'll need to be really careful because one of these numbers is where the function does not exist, and that's the positive 2 value. So we're going to ignore that one as part of our local max, local min. However, we can tell that the -2 would be a local minimum at that location, since the graph goes down and then comes up. So we'll go ahead and put that down here. Local minimum at x equals -2, y equals, going back to the original function, not the derivative, and plugging this in for x, gets us something like -18 divided by 16, and putting that as a decimal would be -1.125. So the coordinate would be -2, -1.125. Now to check for concavity, we need to check for two things. Much like we did for the first derivative, we take the second derivative, check where that's equal to 0, and we also check where the second derivative does not exist. Now again, just for the purposes of trying to understand how to use the second derivative to do these things, I went ahead and put the second derivative down alongside this one so we can have it at our disposal. So without having to go through all the effort of getting there, this will be what our derivative would look like. Second derivative, I should say. If we set this equal to 0, solve for x. Like the last few, I'm just going to ignore the denominator and just solve the numerator. Okay, set that to 0. So basically x plus 4 is equal to 0, and x equals -4 would be one of the numbers. For does not exist, again, we're all focused on the denominator and where it's equal to 0, so the x minus 2. So back to x equals 2 again. So looking at these, then we basically will treat them just like we did in the last step. Choose some test values, check the second derivative. Test values I chose were -5, 0, and 3. And so our intervals -infinity to -4, -4 to 2, 2 to infinity. Okay, and so again, we're plugging these in to check the second derivative. So in this case, y double prime. Our second derivative from up above, 18 x plus 4 divided by x minus 2 to the fourth. And if we plug -5 in here, 18 times -5 plus 4 over -5 minus 2 raised to the fourth power. On top, you're going to get a negative number divided by a positive, so negative, which tells us this is concave down. We plug in a 0. On top, it looks like it should be a positive number. On the bottom, positive. Turns into positive, concave, upward. We plug in a 3. Looks like we're going to have another positive number divided by a positive, so still would be concave, upward. So we only have one location where it changes concavity, and we call that location the inflection point. So we can wrap up our discussion then with this information. This is concave up on the interval between -4 to infinity, and it's concave down on the interval from -infinity to -4. Also, it has an inflection point at x equals -4. To get the y-coordinate, we'll go back and plug this into the original function. 9 times -4 divided by -4 minus 2 squared. -36 divided by +36, -1. So -4 comma -1 is our inflection point. So now we have all this information at our disposal. We can go about sketching the graph of the function. Okay, so here's kind of some of the points that we had from up above. Our inflection point was -4 comma -1, so we'll go and plot that there. Our local min was -2 comma -1.125, so it's just a little bit below the inflection point. And then we had our xy intercept at 0, 0. We have our horizontal asymptote to keep track of as well at y equal to 0, and we have a vertical asymptote, x equals 2. So this graph has to start off decreasing and concave down. So it's kind of concave down till it gets to -4. So it's going to kind of cup downward this way. Then at the inflection point, it goes concave upward till it gets down to the local minimum here. And then it continues to be concave upward all the way through here. And then it's still concave upward on the other side as well. So it looks something like this.